Hello everybody, my name is Matt Skelhorn. I work for Salvage and Marine Operations, or SALMO, in Defence Equipment and Support at the UK Ministry of Defence. First off, I'd like to say thank you very much to the organisers for the opportunity to give this presentation. Unfortunately, I can't attend in person, but I hope you find the following of interest. So today, I'll be talking about the Ministry of Defence Wreck Management Programme, which is the means by which we manage the environmental and safety concerns associated with the oil, ammunition and other pollutants remaining on British military wrecks, mainly left over from the First and Second World Wars. The inventory comprises approximately 5,500 post-1870s wrecks spread around the globe. This slide gives an overview of the wrecks for which we're responsible. In the top left-hand corner is HMS Captain, which was lost in 1870. As mentioned, most of our wrecks date from the First and Second World Wars, and in the middle picture on the slide you can see HMS Royal Oak, a battleship that was sunk in 1939. However, we have wrecks going pretty much down to the present day, and our most recent collections dates from the Falklands War in 1982. Besides purpose-built warships, that is to say Royal Navy and Royal Fleet auxiliary vessels, we are also responsible for a large number of merchant vessels that were taken up from trade and used in an auxiliary fighting capacity. And in the top right-hand picture on this slide, you can see one such example, the liner HMS Dunvegan Castle, which was requisitioned in 1939 and then sunk as a warship in the Second World War. This slide provides an overview of the wrecks lying in northern European waters and gives an indication of the huge numbers that can be found very close to home. While, fortunately, not all of these are MOD owned or pose a pollution or safety risk, it does show the scale of the challenge posed by the wreck inventory. During the rest of this presentation, I'll be discussing what exactly are the risks posed by the wreck inventory and why and how we go about managing them. The main risk posed by legacy wrecks relates to the oil that may remain within them. Now, not all wrecks contain oil. Many ships in the early years of the 20th century were coal-fired, with most Royal Navy vessels of World War I being fuelled in this way. Wrecks of these vessels pose less of a risk than their oil-driven counterparts, and oil became more important over time, and by World War II, most Royal Navy ships were fuelled in this way. It is these wrecks that pose the greatest challenge. Put simply, wrecks of the modern era are large metal boxes, and they decay over time due to a variety of factors on the seabed. As they decay, there is a potential for any pollutants to be contained within them to escape. On this slide you see the battleship HMS Royal Oak, which was sunk in Scapa Flow in the Orkney Islands in 1939. In the mid-1990s, large quantities of oil started to leak from Royal Oak, and it was this wreck that kick-started the MOD Wreck Management Programme. On this slide you can see two photographs which were taken in the late 1990s and which show the oil that was coming off of Royal Oak at that time. Now, the wreck lies in Scapa Flow, a pristine marine environment, and this is obviously unacceptable. So, Salvage and Marine Operations undertook a series of operations or interventions to remove the oil from the wreck. This work continued up till 2009, and currently we monitor the wreck, and at some point we've got to go back and remove some of the oil that's trapped within the deeper tanks on it. When we undertake such work, we have to do it in a very controlled fashion, and we have to take account of the historical and archaeological of the significance of the wrecks, so doing it in a controlled fashion while causing as little disturbance to the vessels as possible. And we also have to take account of the fact that very many of the wrecks we work on are the last resting place of the sailors that died on them. Due to the large number of wrecks that we're responsible for, we have to have a structured methodology for risk assessing and prioritising them. And over the next few slides, I'll discuss how we go about doing that. The wreck assessment methodology comprises three distinct stages. Stage 1 is made up of a historical desk space assessment on each wreck, and an HDBA, as it is known, is a report based on archival information that tells us what a ship was, what it was carrying on at the time of loss, the circumstances in which it was lost, and whether any information is available on what might have happened to the wreck since it was sunk. In turn, this information feeds into what is known as an environmental desk space assessment, or EDBA. The EDBA takes any information gleaned at the HDBA stage on, for example, the amount of oil in a wreck, and models that information to find out what might happen should that oil escape, what areas of the coast it might impact, whether it might impact fisheries or seabird colonies and the like. The information gained at stage 1 allows us to prioritise wrecks for further work, and that then moves on to stage 2. So for a certain number of wrecks, we carry out what is known as an on-site survey using a variety of techniques. Now, I'll go into more detail on this later on, but it allows us to get eyes on a wreck and find out exactly what state they're in. Based on the results of the Stage 2 on-site survey, we may choose to commission an intervention, and that's getting down onto a wreck and physically removing the pollutants from it. And again, I'll be going into more detail on how that works over the next few slides. Before discussing the on-site survey and intervention aspects of the programme, I thought it'd be interesting to discuss some of the background archival documents that are used to compile historic death space assessments. And on this slide, you can see examples of two such documents. On the left-hand side, we have a survivors report from the First World War, and these documents contain crucial information. Survivors were routinely interviewed in both the First and Second World War, and the documents contain information on, for example, what their ship was carrying, the circumstances in which it was lost, where they thought the ship had sunk, and information on, for example, the gun armament of it, so how much ammunition it had on board and the like. On the other picture, you can see a First World War German U-boats logs. And these are also very interesting and useful documents. They can contain useful information on, for example, how many torpedoes hit a ship, or how many torpedoes at least the U-boat commander thought he'd managed to hit the ship with. And this can provide vital insights into how intact the wreck is likely to be at the present day. If, for example, a ship was hit by a single torpedo, it may be in a much more intact state on the seabed, and so therefore more likely to harbour pollutants than a ship that was hit by multiple torpedoes. In addition, the U-boat logs contain vital information on the location of sinkings, and sometimes they can be our only source to pinpoint where a wreck might be. Photographs provide another useful source of information, and it's really surprising how many ships were photographed in the process of sinking in both the First and Second World War. They're useful because they can provide insights into the condition of a vessel at the point at which it left the surface, and this can give an indication of the likely condition of a wreck on the seabed at the present day, and so is useful in the risk assessment process. This photograph on the slide here is a very old example. It dates from the early 1890s and shows the battleship HMS Victoria sinking in the Eastern Mediterranean shortly after being accidentally rammed by one of its consorts. Ship plans are absolutely critical to all three stages of the wreck management programme. At stage 1, they are incredibly valuable for compiling historic death space assessments, as they show, for example, where oil was contained on board vessels and the amounts that were contained in individual tanks, and as we're also interested in the ammunition on board wrecks, where the ammunition was stored in the magazines and the amounts and type of ammunition that were held within them. At the stage 2 or survey stage, they're incredibly useful for navigating around a wreck. Just to orientate yourself on the seabed would be impossible without a ship plan, and it also shows where hazards might be encountered, such as ammunition. For stage 3 or the intervention stage, they are equally critical because we need to know exactly where oil tanks might be located on a wreck in order to conduct interventions and to accurately tap into them to remove the pollutants. In a small number of cases, we may be very fortunate, and a museum ship may provide vital insights into other vessels of the period or of the same class. In this picture, you can see HMS Caroline, which is preserved by the Museum of the Royal Navy in Belfast. Now, we are currently undertaking work on the wreck of one of Caroline's sisters, HMS Cassandra, in the Baltic, and we are using Caroline to inform our work by looking at, for example, the layout of the vessel, the position of the oil tanks, the quality of the build, and the metals used in the construction of the vessel, and the thickness of the metal. And all of this information will inform both the surveying phase, when we eventually carry that out, and, if required, any intervention that may be required on the wreck. Now we've looked at a range of the documents and other sources of information that inform historic death space assessments, we'll move on to stage 2 and look at some of the techniques that we utilise to survey wrecks on the seabed. And we use a large variety of different techniques, with each one tailored to the peculiarities of the particular wreck. And over the next few slides, I'll be discussing what those are. On this slide, you can see what we would term a light survey being conducted on a wreck by the wreck management team using our own in-house resources. The wreck being surveyed lies once again in Scapa Flow, and we utilise one of our own small observation class remote operated vehicles, or ROVs, shown here on the top left of the slide, to conduct a visual inspection of the wreck. In the top middle picture, you can see the ROV being launched, and although the conditions look quite grim, they were actually ideal. The sea was calm and subsurface visibility was excellent, as shown in the 3 pictures on the bottom of the slide. This allowed the ROV pilot, shown at the top right of the slide, to easily manoeuvre around the wreck and gather comprehensive footage to allow us to make an assessment of the condition of the wreck and determine whether it's likely to pose any risk. Besides ROVs, we use other methods to determine the condition of wrecks on the seabed. These range from relatively cheap, light and easily deployed tools to much more expensive techniques, which, however, can provide stunning results. Because of their cost, such high-end techniques are prioritised to those wrecks we assess to pose the greatest risks. On this slide, you can see the results gained from one of the more cost-effective tools, side-scan sonar. Although one of the cheaper methods, the results can still be excellent, as you can see in this image of a World War I cruiser in the Baltic, showing the wreck to be very largely intact. As such, it provides vital information on the likelihood of pollutants remaining on board. On this slide, you can see examples of another technique we use to rapidly and cost-effectively survey wrecks. In this case, a multi-beam echo sounder or multi-beam mounted on the hull of a ship. As a ship passes over a wreck, it uses the multi-beam to build a picture of the wreck below it, which you can see here. While these images are crude, they nonetheless provide useful information on the overall condition of the wreck and are vital tools for aiding their identification. Why is this important? Well, many charted wrecks are listed as either unidentified or have been mistakenly identified. The images you see here allow measurements to be taken of the wrecks, which can then be compared against ships' plans of likely candidates for the wreck as an aid to identifying it. This is critical, as without knowing the identification, it is impossible to know what pollutants may remain on board a ship and so accurately risk assess it. Certain wrecks, such as the collapsed oil tanker shown on this slide, merit the use of much more detailed and expensive survey techniques. In this example, we've again utilised a multi-beam echo sounder, but this time it's been mounted onto an ROV to allow us to get much closer into the wreck and to build up a much more detailed image of it than would be possible with a multi-beam mounted on the hull of a survey ship passing over the top of the wreck. Such surveys allow us to determine the exact condition of individual wrecks and to make much more detailed assessments of the risks posed than would be possible with most of the other techniques. When surveying, we are not just interested in the wrecks themselves, but how they are interacting with their surroundings, and one of the ways we do that is via the use of environmental sampling techniques. In this slide, you can see a core of sediment that's been taken from the seabed near to a wreck, and this core sediment will be sent off to a laboratory where it will be analysed for things like oil and other pollutants that may have escaped from a wreck. This provides us with an insight into how the wreck is interacting with its environment and how it might be polluting it. I'll now move on to talk about stage 3 of the wreck management process. This is the intervention stage where we remove pollutants from a wreck in a controlled fashion before they can escape to the environment. This stage builds on the research work undertaken at stage 1, the historic death space assessment stage, and the on-site surveys conducted at stage 2. The insights gained at the 2 preceding stages are vital for informing and ensuring the success of stage 3. To date, the intervention work we have conducted on wrecks has involved removing the oil from them in a controlled fashion. In the slide you see here, you can see one of our divers undertaking an oil removal operation on the wreck of HMS Royal Oak in Scapa Flow. He's installing what's known as a hot tap system, which is the means by which we burrow into and remove the oil in a controlled fashion from the tanks. The oil is pumped to a tanker on the surface and it is then removed for recycling. In the case of the oil removed from Royal Oak, it went to the local Flotter oil refinery just a short distance away. In this slide, you can see an example of another of the intervention operations we've carried out. In this case, one of our divers is working on the tanker RFA Darkdale, which lies off the island of St Helena in the South Atlantic. Now, with both Darkdale and Royal Oak, we were very lucky. The waters were shallow, and it allowed us to carry out the operations using divers. However, there are very many wrecks out there which lie at greater depths, and these pose far greater challenges when carrying out such operations and may require the use of, for example, remote operated vehicles to carry out the interventions. This slide, again of the intervention to remove the oil from RFA Darkdale, highlights some of the challenges that such work poses with, in this case, the need to rig a platform to allow the diver to safely access some of the tanks on the side of the wreck. As noted on the previous slide, many of the wrecks we deal with in future, lying at greater depths or in more troublesome locations, will provide even greater challenges to overcome. In conclusion, the MOD Wreck Management Programme seeks to address the ongoing risks posed by military wrecks of the present day. While the number of wrecks may appear daunting, the structured approach to risk assess and survey them allows those that pose the greatest risk to be targeted and prioritised for remediation before they can cause major environmental problems.